Okay. So in this presentation, I'm gonna show you how the standards is handling. We are in the standards, we're not doing all this mathematical work. Standards handling in a different way because this is a very long and tedious process. So let's say that you model your building, you select the lateral growth resistance system of the structure, determine the preliminary dimension, which I gave you for the project. And then the next thing is that we need to have a 3D model, like the way that you have it, to apply the earthquake loads. All right, so
Stay.
okay. So what I'm gonna show to you right now, how we perform earthquake equivalent lateral force analysis using the ASC 716. So the first step is to identify where is your location. Is it LA? Is it Wisconsin? Is it Mississippi? Is it Florida? Florida is one of the states that has the lowest earthquake activity. Okay, so we're gonna assume our building, I believe, in Los Angeles. Okay, so we're gonna go to the map. This map, I believe it's in figure 222.2 here. And the standards. So like if you have the standards or a PDF of the standard, or actually you can use this. I'm gonna show you a software that's gonna do all this for us. But this is, to be honest, as an engineer, you should have, as a structural engineer, you should have the ASC 7 that has all the minimum load designs for buildings. Like I would go to the map. Like we have here seismic maps here. Okay, so it's gonna be something like this. And then I'm gonna find out where I am. And then you are gonna find something is called the short and the S1 and SS for the zone that you are in. What is this? This is the earthquake acceleration in this zone. And we get two of them, SS and S1, okay? I'm gonna tell you why we do this. And then we need to have a soil report for the structure. We are gonna assume that the soil that we have is D, type D. There's different type of soils, A, hard rock, B, rock. We're gonna assume that it's D. But in real construction project, we're gonna have a soil report that is gonna tell us what type of soil that we are dealing with. Okay, so once we identify the soil type, we're gonna find something called site coefficient. The site coefficients, we are gonna get two coefficients. One is called short period site coefficient, and one is long period site coefficient. Why we get short and long? If you remember, we have the response spectrum curve. It is like a period from 0 up to whatever number it is. There's a part what we call buildings that has short periods and building that has long periods. Everyone is calculated differently. That's why we get two coefficients. So based on the soil class that you have and the SS that you got from the code, you will come to table 11, and then you will find out what is the FA here over there. And what is the FV? What is the short period site coefficient and the long period site coefficient? We find the two coefficient. We're gonna do step number 4, risk targeted for maximum considered earthquake. So you take these two and then you multiply FA by SS and FV by S1. It's kind of like we need to amplify the acceleration of the earthquake based on the soil. So if you are on a stiff soil, that means your building have less coefficient. If you are on a loose soil, so it's gonna be more coefficient. It's like factoring how the soil is gonna impact the building performance. Then we find a new acceleration for this zone. You remember when I told you an earthquake is hitting a specific area? So we need to find the acceleration, but to find this acceleration, we need to factor in multiple coefficients, the site coefficient, the soil coefficient, and then we take these two and convert them to something is called design spectral acceleration. We multiply the values that we find here by 2/3 to get another set of values. Okay, that's a standard procedure. Okay, but all this is based on research, which is based on the analysis that we are doing here. Okay. All right, and then we need to draw this response spectrum curve. That is the response spectrum curve, okay? So as you can see, it's only one curve, but all the parameters that we are calculating is doing what we were doing, getting points and then making averaging. We need to find one single curve. This one single curve is divided into 4 curves. This one, and this part, and this part, and this part. Depends on how the building is performing. If it has a long period or a short period. So think with me, long periods that mean your building is maybe very, very flexible. Either it's a tall and make like long motion. So tall buildings, like buildings that we are dealing with in our project, it's like 5 seconds. Breathe, okay? But if you have a 10-story, it's gonna be maybe 1 second. If they have 2-story building, 0.1 second to make this motion. Almost very, very small period. So long periods has different calculations. So the codes gives you the equations to calculate each one of these curves. Like tell you from 0 to t, from 0 to tz to to, you are gonna use this equation. It's function in SDS, which we got it from here. And you multiply this by a bunch of numbers. And for part number 2, it's gonna be equal to the S design, it's constant. And then part number 3 is gonna be SD long over the period of the structure. And this is gonna be a different one. So the code gives us all the equation. Why you tell me why I need to draw the curve? If I know the period of my building, I can try to figure out where is it here and go here and substitute in this equation right away and get the spectral acceleration. So that's what the software is doing. But I'm telling you the process of how to build the response spectrum. Specifically, if you are doing a multimodal analysis, you have different T's for the building. So maybe one of the T's are here and one of the T are here. So you need to find the spectral acceleration corresponding to each mode. Okay? And here's defining what is each parameter that you have here. Then the next step is what we call the risk category. So let's say we have a residential building and we have a hospital. Which one is much higher that we need to protect? So it's a hospital, right? So it's have much higher risk category. So multiply the base shear force by a risk factor that is big, maybe 1.2 or 1.5. Okay. So if we have a shelter, like if an earthquake happens, there's places are designed for much bigger forces. We call them as a shelter, like a stadium or a church or something. So we multiply the forces by a risk factor. Residential buildings are multiplied by 1. It's not a high risk category. Okay. So like if you have a special structure you don't know if it's 1 or 1.5 or 1.25, you go read each risk category and try to figure out what is your building fit in each one. Like for example, let's say here, buildings and other structures not included, blah, blah, blah. And here, look at this. Facilities that manufacture, process, handle, store, use, or dispose substances as hazardous fuel or hazardous chemicals. So that needs to be much higher risk category, because if it's like fail or damage, it's gonna affect the environment, right? So I believe hospitals and the one that we have somewhere here, but we try to figure out where is it, okay? So that's one of the things that we need to find out, and I'm gonna tell you where we are gonna use it. Okay, so the next thing, actually, that's an interesting point. There's something called seismic design coefficients and factors. I don't know if I have time or not, but okay. So when we design for seismic is a really huge force. Like if it hit a building, this building is like it's a huge force. But there was 2 concepts to design for seismic. Either to make the building very, very stiff, like very, very strong. If it's gonna hit by an earthquake, it's not gonna move. But if it got damaged and failed, we have a big cross sections, okay? It's gonna be a disaster, okay? Or we are gonna make our building flexible. Like, okay, if the earthquake hit, I'm gonna allow some damage, but it's not gonna lead to failure. Maybe we are gonna have some cracks. So it's either you make your building elastic, like if the building is moving, it's gonna come back to its original position without any cracks. We call elastic design. But this design is very expensive and the damage is gonna be very bad. Or we make it as an inelastic design, like the building is gonna move and we are gonna allow the building to have elasticity. Like we are gonna have some cracks and it's gonna open and it's gonna return to its original position, but it's not gonna fail. And after the earthquake, we are gonna repair it. So it's gonna allow us to design the building under low seismic force, okay? And this is less expensive design. So what we are gonna have is gonna be something like this, right? So let's say we are gonna capture the delta of the building with the force on the building. The elastic design, if an earthquake hit the building with elastic design, we need to have a linear relationship, like as the force increase, delta is gonna increase, is gonna be something like this. Let's make the line. We're gonna have, for example, something like this, okay? So once an earthquake hit a specific force and the earthquake is gone, this building is gonna return to its original position. There is no inelastic deformation, okay? So if elastic is something like this, right? And the maximum delta that the building is gonna reach is gonna be something like this, all right? So there's elastic energy, like the energy are like the earthquake energy pushed the building, it dissipated into deformation, and then the building restored the deformation back once the earthquake is gone. But there's another way that we can design the building in much lower force here. But the thing is, this building, the maximum elastic force that it can take based on the stiffness and the masses of the element is up to here. And once the force exceeds this limit, you are gonna have inelastic deformation. Like building cannot offer more forces than this. And it's gonna keep deforming, like cannot take many forces. Both systems have the same energy, but this one, some of them is elastic and some of it is inelastic energy. This one have all of it as elastic energy. So we call this F inelastic. You know, it's something like back in the days when they were designing cars, the cars was like a box of metal. Like it's really, really a huge box of metal. Metals are everywhere. Right now, cars, it's more plastic. Like if like back in the days, two cars hit each other, you will not find a car is compressing this way. Like it's like a very, very strong cars. But right now, it's more elastic. So how's the two different design concepts? So rather than having the driver absorb all the energy of the impact, you make the car deform and absorb all the impact into deformation. That's the same thing here. You make the deformation into this. And this allows us to reduce the seismic load. Can you imagine? Sometimes R equal to 5 times. Like let's say without R, you are gonna have 1,000-ton base shear in the building. But if you allow inelastic forces, you are gonna make this base shear to 200. That can you imagine how much the cross section is gonna be decreased 5 times? Okay, it's not linear, but I'm telling you, it's like 5 times reduction. So we call R is the ratio between the F elastic and the Fn elastic. Okay, so that's the concept of reduction factor. Okay, so yeah, I mean, I'm not gonna go much in details because I don't have time, but this is a little bit of introduction about the response modification factor, which is R. And one other thing, I told you that the T depends on the mass and the stiffness of the structure. The standards has another equation that calculates T, which is a simplified one, but it's not the exact one. If you want to find the exact one, you need an app like a software, analysis software, calculate all the masses, all the stiffness, and find the actual T. But this one is an approximate one as a function of the height of the building and the system, the structural system that you have. If you have a frame, if you have shear wall, you have a steel, concrete, each one is different. That's a CT multiplied by HN multiplied by X. So let's look. There's a table that tells you if your building is a moment resisting frame, or your building is a steel moment frame, or a concrete moment resisting frame, or there's a shear wall. I believe here is the all other structure system, which is a shear wall. So you're gonna pick this number. This is the CT, and this is the X. You go back, substitute in your equation, and you are gonna find the natural period of the structure. So standards provide you with some simplified equation that doesn't, like before you run the analysis for your software, substitute in this equation, find what is the value of T, and build a model and see what is the actual value of T. Okay, so we have this, and then we substitute, and then we are gonna find what is the T for the structure. Okay, so one other thing that we are gonna do as well, since we are gonna design that our building is cracked, like we are gonna allow our structure to have inelastic deformation. What does it mean by inelastic deformation? That all the sections are gonna crack. Like if the building is having inelastic deformation, that means it's not gonna return to the same position, and sections are gonna open and gonna be cracked. So you need to model your cross section as a cracked section, not as a full cross section. How we can do this? The codes provide some stiffness reduction based on seismic design. If you are going to do seismic design with inelastic deformation, so you need to model all the cross sections in the buildings as a cracked section or as reduced stiffness section. So doing seismic analysis, we reduce the stiffness of the column by 30%. So we assume that the columns are working at 70% efficiency. Walls, depends on actually in walls, there's something called cracked and uncracked. It's like excessive cracking if we allow an elastic hinge at the end of the wall. But let's say we're gonna go with uncracked, like the columns 0.7. Beams is 0.35, slabs is 0.25. So when we do seismic analysis, we are gonna reduce all these systems. Okay, all right. And here it tells you how to calculate the forces. I told you that we're going to calculate the forces, the base shear here, V at the base of the building. But we need to find out what is the contribution of each story from this base shear. Like when you shake the building from the foundation, like this, all the masses are going to move, right? We need to find what is each story is absorbing, what is the value of the force or the contribution from the base shear that each story is absorbing. And this depends on the height of the story and the mass of the story. If a story that has a big mass is going to absorb more force. And if it's at a higher elevation, it's going to absorb more force. Okay, so the code gives you actually the equation that can calculate the total base shear. So here you have something called CS. Okay. Yeah. So what we want to find out is V, right? V is CS multiplied by the weight. I told you like V is a force. It should be multiplied mass and acceleration. Well, mass is inside the weight here, right? Because the weight, the mass is the weight over G, right? So definitely G can be inside this factor. And the acceleration is going to be inside this CS. So basically CS is an acceleration. It's called the seismic response coefficient determined in accordance with this section. And it has acceleration inside it. Let's see how's the acceleration inside. It has SDS, which is the spectrum design acceleration that you get it from the responsive spectrum, divided by R. R is the reduction factor. So the acceleration is divided by R. That means that we divide the whole force by R. Multiplied, like IE should be on the top, by the risk coefficient. Okay, so when you divide by the IE can be, that makes this like, if this value is bigger, if the risk coefficient is bigger, like 1.5, so the 1.5 is going to go up and make the forces much more. So you divide by R to reduce the forces, and then you multiply by the risk factor to increase them back, depends on the risk coefficient. And here it gives you different ways to calculate them based on the natural period. If the natural period is less than TL, it's more than TL. So I know standards has a lot of equations, but this is how buildings are designed. Yeah, this is analytical solutions, and there is a standard solution. If you design the building, you are not going to go this way. You are going to go with the standards way. And there's softwares that can do this for you, but it's better to understand analytically how this came from, and you better to understand how the standards are dealing with them. Not because I'm going to show you next time in ETAS how all of this can be done in 2 minutes. Find the soil, define everything, and the software is going to do everything for you. You are not going to do anything, but I need you to understand what is behind this going in software, because if something goes wrong, you need to find out what is each factor is affecting what, okay? All right, so I believe once you find the base shear, the next step is to distribute V over the stories. So basically we find something like that the Fx is the story force, and V is the total base shear. And this factor is the contribution of each story. Like Fx has a contribution of Vx, like let's say it's going to take 0.1%. How to find this value? You multiply the weight of the story by the height of the story to the power 1 or 1.1, depends on the system, and divide it by the weight of each story multiplied by the height of each story. It's like a weighted average, okay? The weighted average of the height and the weight. Okay, so this is how we do this. We are not gonna get in details how we find the equivalent forces, but if you are having a seismic course, you have to do all this manually, like you know how to do that. In our course, we're gonna do this by e-test. So I believe that's it for now, and I believe you try to chew on this information, understand what we are doing. And next time, I'm gonna show you how to apply the forces on ECAPS so that we can start the project. I believe last time is the last lecture for the project. Maybe we have one more lecture if we were not able to cover everything, but just one or two lectures, then we will get back to structure. Okay. All right, see you guys next time. Yeah, that's something that we can do, and we are gonna do this in a step by step, but in the buildings, you can do this, but when you have like whole buildings, like we usually, since we can model the whole building, I didn't see that you. And any of our models, we cut the building, and we make about.
Because you have to do a lot of time.
Yeah, that's all. But the thing is, we usually apply earthquake and X direction, earthquake and Y direction, so. Like, it's like you say an earthquake and X is hitting, and there's another one hitting in Y direction. So we say, all the earthquake and X and 0.5 Y, 1 Y and 0.5 Y.
Geometry is good, but then maybe symmetrical, but then you're not building the same.
Yeah, we can do that.
Yeah, that's also one of the things. And from financial perspective, lateral load analysis, when you run your building is not gonna take much time. Since we are doing the diagrams, using freedom, and increasing the mesh size of the slab, so it's not like the slab system that has lots of points. It's just, what is the software take much time, and the moon shape constellations, and combining them and solving the matrix, like since you have a multi-degree freedom, the matrix for the mass, matrix for these matrices. So it's more dynamic analysis rather than finite.
So things, it makes sense.
Right.
But you're not gonna integrate, so.
Yeah.
But you can. Yeah, the one you were pretty much, we have the same.
I have to do something. It'll, do things in five o'clock, right? Thank you.
I sent you the email again.
Yeah, I just got it this morning. Thank you.
Doesn't, you know, which. So, just.